This is AP Calculus BC, and in this video I'm going to talk about section 9.4. The title of this section is Convergence Tests, and we're going to talk about some new tests for convergence in addition to the things that we looked at in 9.3, where we talked about geometric series and we talked about telescoping series. So today we're going to talk about something called the nth term test, which is also sometimes referred to as the test for divergence or the divergence test. We're also going to talk about the integral test and the p-series test, which is really just a specialized version of the integral test. So remember last time when we went through geometric series and telescoping series, we could always find the sum of the series. Well, the reality is most of the time when we have an infinite series, we can't find the actual sum. So usually what we're trying to do is we're just trying to find the behavior of the series. For the purposes of what we're going to do when we get to the end of the unit, we're talking about Taylor series to model a function. We just need to know, does our series converge or does our series diverge at certain points? And so testing for convergence is really what's more important to us than finding the actual sum. And the first test we're going to look at is called the divergence test, or I refer to it as the nth term test. And like I said, sometimes you'll see it referred to as the test for divergence. It just depends on the book that you look at. But the main thing is this is pretty simple. The idea behind this is a way for me to know for sure immediately if my series is going to diverge. And it just involves looking at the individual terms. So we're essentially looking at the sequence of terms and seeing if the sequence of terms approaches zero. Because if the sequence of terms doesn't approach zero, as I'm adding those terms together, if I get to the end of my series and I'm still adding more and more value, like let's say my terms converge to a value of 1, then at the end of my series, it's essentially going to say plus 1, plus 1, plus 1, plus 1. And so that sum of my series is going to keep increasing forever. So what I need to be happening is that I need my terms to be approaching 0 in order for me to know that it's even possible for the series to converge. Okay, so for example here's a couple of sequences. You can see that side by side, we've got two sequences that are converging to 0. So if I were to do the test for divergence, at this point, I would know, okay, this possibly converges. So I'm going to have to do more tests. And that's really what the test for convergence is, or excuse me, the divergence test or the nth term test. That's really what it's for, is kind of a pre-check. Now, look at these two sequences. They look kind of similar, right? Both of them have terms that are approaching 0. One of them, it's 1/2, 1/4, 1/8, 1/16, 1/32, and so on. The next one, 1, 1/2, 1/3, 1/4, 1/5, 1/6. Well, you might recognize the one on the right there. That's our harmonic series, and we talked about why that series is actually going to diverge, even though the terms are approaching 0. Well, take a look at the partial sums. So if I were to go through and add a few of the terms together, you can see with the sequence on the left, the partial sums look like they're approaching a value of 2. If I look at the sequence on the right, the partial sums keep getting bigger and bigger. It looks like maybe I'm approaching something, but if I kept listing them out, you would see eventually that the sum keeps getting larger and larger and larger. So in the end, it turns out that the series that uses the terms in that sequence on the left, that one is going to converge, and the one on the right actually diverges. And again, remember the one on the right was the harmonic series, so we kind of know why it diverges. The main idea is I can't just look at the terms and see that they approach 0 and know that my series is going to converge. The only thing I can tell by looking at the terms and seeing if they approach 0 is that if they don't approach 0, I know for sure the series is going to diverge. So that's what the nth term test is. Okay, so take a look at theorem 9.4.2 here. If the series converges, then as the term number increases infinitely, my terms should be approaching 0. That's essentially what that theorem says. Kind of goes without saying, but it's actually stated within a theorem there. So here's our divergence test or our nth term test. So if I take the limit of my terms and they do not approach 0, I know for sure the series diverges. Now, where people misuse this is that they think they can make another conclusion with the nth term test or the test for divergence or the divergence test. So the second part of this says, if the limit of the terms does approach 0, then the series still could converge or diverge. So at that point, I have to look at some other methods of testing for convergence. Okay, so let's take a look at how we would actually implement the nth term test. So when we use this, it's really just a matter of solving a limit. A lot of times you'll do these in your head, but I do want you to get in the habit of just showing the limit. So it says use the nth term test to determine the convergence of the following series. So what I'm thinking about here when I'm actually using this test is I'm thinking about, I guess I moved down too far here. I'm thinking about actually going through and thinking about, okay, what's the limit as n approaches infinity of n over n plus 5? Well, that's actually equal to 1, right? Because the degrees are equal. We can kind of see that pretty easily. So with that being the case, I know immediately this diverges because my terms are not approaching 0. So it diverges, and my reason for that is the nth term test. So one of the things that we're going to do when we are showing convergence or divergence for a series is we're going to show a justification. So in this case, when I use the nth term test, my work to basically justify my use of the nth term test is that limit. So I need to show that limit, and that limit is essentially what's telling me that it is okay to say that this diverges. Now let's take a look at this second one. If I were to take the limit of these terms as n goes to infinity of n over n squared plus 1, I do get 0. Now remember, that doesn't necessarily mean that this converges. That just tells me that it's possible this converges. So it actually turns out this one diverges. We'll talk about this way down the road. We could do a very easy limit comparison test on this one and show that this diverges. But at this point, all we know by looking at the limit of the terms is that this either diverges or converges. Okay, so we would have to use another test to determine whether or not this is going to diverge or converge. So like I said, in this case, I would probably use a limit comparison, and we'll talk about that in another couple of classes. Okay, so that's really the main idea. So every time when you see a series, the first thing you should always do is the nth term test. So you may even just do it in your head sometimes. Just immediately think, okay, does the limit of the terms approach 0? If not, okay, I know it diverges, and then we can justify that. If the terms do approach 0, I don't need to actually write the limit out. I would just move on to whatever test I'm going to use to show convergence or divergence. Okay, so the next test we have is called the integral test. And I mentioned this one a while back when we were doing improper integrals in the first unit of this semester. So the integral test is based on the idea of an improper integral. And so we're kind of comparing a rectangular approximation and an actual integral value. So what we're doing is we're essentially saying if we have some series and the terms in that series follow the same rule as some function, if we were to take the integral of that function from whatever term number we're starting at to infinity, if that integral converges, then the series also converges. Now, you might kind of question why when you first think about that, but if you see graphically, it kind of makes sense. This is the graph I really like to use. Okay, so I'm kind of looking at this as a left-hand approximation here, and this is the way I like to think about this. So when n is 1 to n is 2, if we're thinking about approximating the integral, the actual rectangles here are the same thing as the terms in my series. Because when n is 1, I get, whatever the value is of that first term. Well, from a rectangle standpoint, notice we have a base of 1 here, and we have a height that's equivalent to whatever that term value is. So if I were to get the area of that rectangle, it would be the same thing as the first term in the series. So as I add these up, these rectangles are essentially the sum of my series. Well, also notice, if we were to use the same rule that we're using to represent where these function values are coming from, if I use the same rule and I integrate, the area underneath this curve is essentially what those rectangles are approximating, right? We're doing a left-hand approximation of the area under the curve. So in order for that area to converge, these rectangles have to be converging to some value, or vice versa. If my integral is going to converge, then those rectangles are going to converge when I add them all together. So that's really the idea behind it. And we can do the same thing with a right-hand approximation. That's what they're doing here. It's still the same kind of idea, but we typically look at it with a left-hand approximation. Okay, so let's look at how do we actually use the integral test. Well, this one's really easy to use because all you're really doing is solving an improper integral. And remember, I told you back when we were doing section 7.8 on improper integrals, I told you that this is something that was going to be a really big deal for us in the series unit. And it is because it's one of our most basic convergence tests. So if I want to see if a series converges, and if you remember the p-series test, you may be already able to tell that this converges, but for now, let's just go through and do these with the integral test. So I've got 1 over n squared. So all we have to do is say, okay, if we were to add up all of those terms, that's going to have the same behavior as the integral from 1 to infinity. And you can use x if you want. I usually just use n, as if I integrated 1 over n squared dn. Okay, so now all I have to do is essentially solve this improper integral. If this integral converges, that means my series converges. If this integral diverges, that means my series diverges. Okay, so remember when you solve these out, don't forget to be really good with your notation here. So I'm going to convert this to a limit and make this the integral from 1 to t of 1 over n squared dn. And now I can solve this out. So this is still the limit as t approaches infinity. My antiderivative, remember this is essentially n to the negative 2 power. So my antiderivative would be negative 1 over n. I'm going to evaluate that from 1 to t. And now I'm going to actually plug everything in. So I've got the limit as t approaches infinity. And I'm going to have negative 1 over t minus negative 1, so plus 1. And now I can apply my limit. And when I take the limit as t approaches infinity, you can see that that negative 1 over t term is going to approach 0. So we get a value of 1. So we ended up with a number that is finite. And so the integral actually converged. So since the integral converges, that means this series also converges. Okay, so let's go back and talk about one thing that we have to be careful about when we're going to use the integral test. Remember, the whole idea of the integral test was that we've got a function that is behaving in the same way as a rectangular approximation. And so in order for this to work, see how my rectangles are getting shorter and shorter and shorter as my area, the heights for the rectangles are getting shorter and shorter and shorter as my kind of distance between the x-axis and the function is getting smaller and smaller. So this is only going to work when I have rectangles that are decreasing in size, and it's also only going to work when I have function values that are positive, because I have to see that same behavior where the terms are approaching 0 as the function approaches 0. So there is one thing that we have to be careful about when we use the integral test, and that is if we use the integral test, it has to be a function that is decreasing and continuous on the interval. So we have to start with typically positive terms because we're dealing with a series that we're trying to find convergence for. So if you didn't have, like, let's say all the terms were negative, you could just factor the negative out and turn it into all positive terms. But the main idea here is if you have a function then that is decreasing and continuous on your interval, then you can use this. So make sure you've got terms that are actually decreasing in value. I mean, if the terms weren't decreasing, we already know that it's going to diverge. But that is one of the criteria we have to meet for the integral test. Okay, so let's take a look at this one. Now, well, I'm going to have you work through this one. But before we do this, I want to start to get in the habit of going through kind of our pre-steps. So when I say pre-steps, what I mean is just thinking about the nth term test every time we see a series. So the first thing I do when I'm trying to figure out if a series is going to converge or diverge is I actually just look at it and think, okay, do the terms approach 0? A lot of times it's very obvious and I don't even have to solve the limit. I can just do it in my head. Like, for example, on this one, I can see that the terms are going to approach 0 as n gets infinitely large. So what I want you to do, and really I want you to do these next two, is that I want you to first verify that the terms are approaching 0. So it could possibly converge. Then I want you to think about, okay, is this a function that's actually positive and decreasing in value? And if so, then use your integral test and try to figure out whether or not these two series are going to converge. So I'm going to pause the video and let you work through both of those. And then when you come back, I'll show you the solutions. Okay, so here's what you should have ended up with on these two problems. You can see they both converge. And again, you do your nth term test. We know that it's possible they both converge. Then, in order to identify, is this a candidate for the integral test, I really look at, first of all, are the terms decreasing in value? Are they approaching zero? Yes. So then I go through and actually solve the integral out. And you can see on the first one, it was pretty straightforward. It's just an inverse tangent. And we actually had the integral converge to pi over 4. That tells me my series converges. Now, keep in mind, because my integral converged to pi over 4, that does not mean the sum of my series is pi over 4. Remember when we looked at that graph a minute ago, the rectangles and the function, the area under the curve had similar behavior to the sum of the rectangles, but they weren't exactly the same. So it's not like when we're doing rectangular approximation and we're taking the limit as the number of rectangles gets infinitely large by making the width of the rectangles very, very small. What we're doing now is we have an infinite number of rectangles that always have a width of 1. So we're always going to have error difference between the integral and the actual sum of those series terms. Okay, so then for the second one, same idea. You can see this one involved the u substitution. And still fairly simple. Don't forget to use your proper notation. Make sure you write the limits out and then work through the process here. Not super difficult, but in the end, I got a number that's essentially 1 over 2e, and that converged then because the integral converged. Now, a lot of times with these, you're going to use different integration techniques. You might see integration by parts, substitution like we saw here. On rare occasions, you might see some partial fractions. Usually, if there's partial fractions involved, we've probably already checked to see if it's a telescoping series, and so most of the time partial fractions won't show up. But you will see some integration, different integration techniques showing up within these problems. Okay, so I will tell you this. The integral test is kind of tedious, and it's one of the ones that once we learn all of our tests, so we're going to have 10 ways that we can check for convergence or divergence of a series. The integral test is usually my last option, primarily because there's a lot of work involved. There's a lot of steps involved in solving one of these improper integrals. But there are situations where there's no other way to do it than to use an integral test. But like I said, usually I try to work around that as much as possible. So one way we can work around it is to use the p-series test. And we talked about this when we were doing improper integrals. The idea with the p-series test is that if I am looking at the sum of a series that has the form of 1 over n to some power, and both of these should actually be n's. Let me rewrite these as n's. So this should actually be an n, and this should be an n squared here. But if I'm looking at series that are in this form, remember, if the exponent is less than or equal to 1 on that n, I know it diverges. If the exponent is greater than 1, then I know the series converges. So it's actually just a shortcut for the integral test, because if I went through and solved the integrals, like we just saw up here a second ago, 1 over n squared, we saw that it converged when we actually solved the integral out. But what the p-series test allows me to do is not have to solve that integral every time when I have series rules that are in the correct format. Okay, so this is kind of my general rule then. So if I've got this form 1 over k to some power or 1 over n to some power, whatever you're using as the index, then you can go through and just essentially look at that exponent, and from the exponent we can figure out convergence. So you can see we've got 3 problems down here below, and these require, if they're in the correct form, they require almost no work. So 1 over n to the 5/4 power, that converges because of the p-series test. You can see the exponent is greater than 1. The second one, essentially 1 over n to the 1/2, you can see it diverges because the p-value is less than 1. And then we've got 2 over n to the fourth, which again is going to converge. Now notice we don't have a 1 in the numerator, but you could just factor the 2 out of the summation. So even though we've got a 2 there, it doesn't make a difference in the end in terms of the p-series test. So since I have an n to the fourth, I know it's going to converge by the p-series test. So it's a very, very easy test to use when it's appropriate. So this is one that you have to really, really have down, because when we get further along, we're going to talk about some comparison tests. Eventually, what we're going to do is we're going to take a series like this. Rather than doing an integral test, I'm going to be able to compare this. And when I do a comparison, I'm going to compare it to a p-series. And then if I know the p-series rule, I can figure out and show that this converges in just a couple of steps using a really, really easy comparison process. So the p-series test is probably the most common test that we're going to use to show convergence. So make sure you've really, really got that one down. All right, so let's talk about one other thing here. When we use the integral test, remember we talked about the idea that the series is sort of behaving like a rectangular approximation of the integral. So what we can do is we can actually figure out how much error we could possibly have if we only use a certain number of terms in our series to add up that series and approximate what the sum of the series is. Okay, so for example, and I'm going to come back to this in just a second. So this is the idea that we're going to use, and we're really only going to use 1/2 of this. But when you see r sub n, that's talking about the remainder after a certain number of terms. So we'll come back to that in a second. So let's look at this. It says use 10 terms to find the approximate value of 1 over n cubed. Okay, so we have this series starting at n is 1 going to infinity. So what we're saying is that let's go through and say the sum of this series from n is 1 to infinity of 1 over n cubed can be approximated by just using the first 10 terms. And so what we're kind of thinking is once we get past n is equal to 10, these are getting really, really tiny, and it doesn't make that much of a difference anymore depending on the accuracy that we need, right? So if I were to do this and just add up the first 10 terms, I'm going to get about 1.1975. Let me rewrite that. It's a little sloppy there. 1.1975. Okay, so that is essentially what I'm saying. My series is roughly adding up to about 1.1975. Now, what I want to know is, okay, if I only use that many terms, I've left off term 11 all the way to the infinite term. How far off could I possibly be? And so that's what we have up above here is saying, okay, based on knowing that the series sum is behaving in a similar way to the integral, we can approximate how far off we are by using that integral value. So I'm going to go back to the diagram we were looking at before and just show you kind of an example here. So let's say I added up the first 3 terms in this series, and I wanted to know how much error could I possibly have after the first 3 terms in the series. Well, notice if I took the integral from 3 all the way on here. So if I found all of this area, and let me do it in blue so it kind of stands out here. If I found all this area in blue, that area is a little bit less than all of the remaining rectangles, right? So I added up the first 3 terms, and now what's underneath the curve f of x from 3 on, that area is a little bit smaller than the remaining rectangles. So that's what I'm going to do here is use that idea to actually show how much error I have. So when we look at these error calculations, you can find an upper bound and a lower bound by thinking about like a right hand and a left hand approximation. We're primarily going to use this half of the error bound. We want to show that our remainder is less than some number typically. So let's take a look at the second part of this question. So it says, if we were to use the first 10 terms, let's see how far off we actually are. So I've got this integral going from 10 to infinity. And I'm doing that because that's the upper bound on my error, right? It goes from n to infinity. Whatever term number I stop at, that's where I'm going to start my integral. So if I integrate from 10 to infinity, the same function rule, 1 over x cubed, I get 1 over 200. So that's telling me that those remaining rectangles, the ones that I haven't added up yet, those have to be smaller than 1 over 200 because that's what the remaining integral value is. So the error then is at most 0.005. Now, if we went one further, then we can also find a lower bound, and then we can kind of have a range of values of what the error is. We don't know the exact error, but we can get a range of values. So for us, I'm typically just going to focus on the upper bound of the error, so we have a general idea of how far off could we possibly be. Okay, so again, whenever you're thinking about those error calculations, you always want to be thinking about these rectangles. So thinking about the rectangles versus, finding the area underneath the curve. Okay, so there's one other type of problem here that involves error that you're going to see, and this is how we would actually use something like this. So it says use the integral from n to infinity of 1 over x cubed dx equals 1 over 2n squared to find the number of terms required for the sum of the series to be within 0.0005 of the correct answer. So that's basically guaranteeing that I have accuracy out to the third decimal place, because if I'm less than 0.0005, then I'm essentially bringing rounding for the third term into play. Okay, so what I'm saying then is looking at that same series that I had before, right? The 1 over n cubed series. How many terms would I need to get the accuracy that I want? I essentially want accuracy out to the third decimal place. Well, this is telling me if I stop at a certain number of terms, this is what I'm going to end up with as the error. So if I stop at some term, if it's 10, like on the last one, we had 1 over 200 because it's 1 over 2 times 10 squared. Well, what do I have to stop at so that I get a number that's less than 0.005 or 0.0005? Okay, so remember, 1 over 2n squared is the error after n terms. So what we're saying, if we want our error to be, or we want our sum of our series to be within 0.0005 of the correct answer, we're saying we want 1 over 2n squared to be less than or equal to 1 over 2,000. That's what 0.0005 is as a rational expression. Okay, so now I'm going to solve this out. Essentially what I'm saying here is n squared has to be greater than or equal to 1,000. And then I can just, look at that on the calculator, or you can just think about, well, that means n is greater than or equal to the square root of 1,000. Well, that's going to give me a decimal. That's 10 root 10, which is about 31.62. Well, remember, n for us is a term number. So we can't have 31.62 terms. So clearly, we're going to have to round up here because we want to make sure our error is smaller. So we want to use more terms rather than less terms. So we're going to round up to 32 terms. So that tells me if I want to get accuracy out to the third decimal place, I would have to use 32 terms in this given series to get a good approximation for the value. Okay, so that's kind of the idea. That's how the error works. Now, getting a total of 32 terms, that's not typically how our series are going to work. When we're writing series to model functions, we're usually going to use like 3 or 4 or 5 terms to get accuracy, a lot of times out to the 5th or 6th decimal place. So 32 terms, is not really a realistic number of terms to use to approximate a series. But this is just kind of getting you used to the idea of how it works. So keep that in mind. 32 terms is not a very practical number. Okay, so as you work through the assignment, these are all of the things that you're going to see. So you're going to see the nth term test, you're going to see the integral test, you're going to see the p-series test, and you're going to see some of these error calculations. Now, I only went through the upper bound for the error. Remember, there's this other part for the lower bound, and you may see a little bit of that in your assignment, but as it pertains to quizzes and tests and that kind of stuff, we're only going to be worried about the upper bound. So that's really the part that you should be focused on when you're looking at the error calculations. Okay, so next time we'll get into some more tests, but remember, like I said before, that p-series test we're always going to be referring back to. So more than anything, and the good thing is it's the easiest one, more than anything, make sure you really understand the P-series test and know the shortcut for that one.